algebraic expression and an algebraic expression, we just say that they're equal. We say 9n minus 11 is equal to 7n plus 11, and then we just solve it algebraically. So I'm going to subtract 7n from both sides. In the same step, I can also add 11. So over here, the 11s are opposites, they cancel. Over here, the n's are opposite, they cancel. And then we're left with 9n minus 7n, which is 2n. And over here, we have 11 plus 11, which is 22. So when we divide by 2, we get n equals 11. And it feels like we're done, but we're not. Because we got to plug that back in, right? We got to figure out what is the measure of WS. Okay? So I need to take that 11 and plug it back in. Does it matter which one I plug it into? No, because they're congruent. So pick the easier one. Whichever one looks easier to you, looks like less math, pick that one. But in this case, they're about the same. So I'm going to do 7 times 11 plus another 11. So 77 plus 11 should be 88 degrees. What's the other one going to be? 88 degrees. Okay. Any questions on example number 3 there? All right. Let me move that up. Now we're going to talk about theorem 11-2-3, which is also on that list of theorems. It's right underneath the one we just looked at, right? And here's what it says. 11-2-3 that says, in a circle, if a radius or diameter is perpendicular to a chord, then it bisects the chord and its arc. Okay, so here's your radius going from C to D. See the little box? Little box means it's perpendicular, means it's 90 degrees, right? If you've got that, then that radius is going to bisect that segment, making those two tiny little pieces equal to each other. So this little piece and this little piece will end up being the same. 11-2-4 is just kind of the converse. It says, in a circle, the perpendicular bisector of a chord is a radius, or if you draw it all the way through, ends up being a diameter. Okay? So we're going to draw a little picture of it in your notes. So just title it 11-2-3 for now, because it doesn't really have a name. Start by drawing your circle. We'll call this circle C, and just go straight down to draw your radius. So there's radius CD. Now, as nicely as you can, draw a chord going across and label it EF. This is going to be perpendicular, so we're going to put that little box there. And since this is really 2 theorems, but they're just converses of each other, we're going to call them 1 and 2. The first one says, if CD is perpendicular to EF, then that CD is going to bisect EF. Cuts it exactly in half. And the 2 smaller pieces become congruent to each other. Okay? The converse of it, or the second part of it, says that CD is the bisector, is the perpendicular, if CD is the perpendicular bisector of EF, then it is a radius, or if you draw it all the way through, ends up being a diameter. Either one, radius or diameter. Okay? So let's look at the practical application for it. Problem with that in there. Okay, which will be example number 4. It should be your last box. So always start with the circle. And we've got circle R right here. And from R, we're going to go over to the side, making it a radius to M. We're going to dash in another radius over here to N. And then N to the other side of the circle is going to be our chord at P. And just for naming this intersection, we'll call that S. And put a little box because that's what the theorem says. The theorem says they're going to be perpendicular to each other. Okay? So they're going to be perpendicular. We indicate it by the little box. And then from R to S is going to be 8 inches. And from S to M is going to be 9 inches. Obviously not drawn to scale. And we're going to find NP, the length of this whole chord right here. Okay? And so when you first look at this, you're like, oh my gosh, this looks super complicated. I don't know if I can ever figure this out. There's nothing even on NP. There's no measurements given to me at all, right? So we're just going to go from N to S, and we're going to say just that little piece we'll call X. And I'm going to make this into a triangle. Look, RNS makes a triangle right here. And it has a little box in it. So it's not just any triangle, it's a special triangle. It's called a right triangle, right? And right triangles, we can use what theorem on it? Pythagorean theorem, right? So this leg is 8, this leg is X, and we come over here to this hypotenuse and we go, oh, we need a measurement there. But aren't all radius the same measurement? Right? You see how R to N is a radius? What about R to M? Also a radius. How long is R to M? 17. So we're going to write 17 inches over here. And we're going to use the Pythagorean theorem on it. So we're going to say this leg, which is X, square it, plus this leg, which is 8, square it, is equal to the hypotenuse, which is 17, square it. Then we just simplify. So X squared plus 64 is equal to 289. Subtract the 64 from both sides, and our X squared is 225. Do we like 225? It's actually a perfect square. Does anybody know what the square root of 225 is? 15. So this much of it is 15. Guess how much this much of it is? 15. So NP is equal to 30 inches. We just add those two together, and that gets us the full length of that chord.